Hey everybody, welcome back to a web lecture. Hopefully this helps clarify anything that might be misunderstood or missed from class, and we'll make this concise as possible. So the law of chemical equilibria, having caught up with the first lesson in module 1, you would have went over what the conditions for equilibrium are and what equilibrium is, and the fact that it differs from what you've learned before because it's a two-way reaction versus a one-way. So what we recognize is that a one-way reaction has the arrow pointing towards the right, the products, versus an equilibrium reaction, which has the arrow pointing forwards and backwards. Okay, meaning that the products can turn back into the reactants, not just going in one direction. So that's what we're going to focus on here. So we'll do this in two parts. The first part will be the theory behind the mathematics, and then I'll have a separate video posted up going over the actual calculations related to this. So we're going to look to describe what the equilibrium law is, and then describe the state of the equilibrium in terms of the product and reactant concentrations based on the value of K. So the definition is stated here. At equilibrium, there's a constant ratio between the concentrations of products and reactants in any change regardless of initial concentration. So what that means is that when the reaction is finished, there will be some reactants left and some products, and we use those graphs in the first lesson. So time, concentration versus time graphs. We lost reactants and we gained products. Okay, so if that's reactants and that's products, right, the ratio of these two for a specific reaction will always be the same regardless of what the initial concentrations were. Right, so we can double those concentrations. At the end, they will be that far apart still. Okay, so there are many scenarios those lines can overlap. The products can be above the reactants, and those are outlined in the first module as well. So the equilibrium law itself is outlined here. For a reaction, A plus B produces C plus D. Right, the equilibrium law can be expressed as K, which is a constant value, is equal to concentration C times D divided by concentration A times B. You'll notice that the coefficients are the exponents in this case, because we're looking at reversible reactions where the products turn into the reactants, and we're looking at these specific reactions here. Okay, so we will be using the coefficients as the exponents, unlike what we did with rates where we had to determine them. So a nice way of remembering this is products over reactants. Just a little ratio for that. Okay, and it's a little helpful guide. Mathematically, it means nothing for us, but if we apply this actual formula, it gives us something to calculate with. So some notes before we move forward. The concentrations are equilibrium concentrations, not initial. So that's important. Okay. We don't include solids or liquids. So in terms of states, right, a gas or an aqueous substance will be found in here. Solids or liquids will be not. And we replace that value with 1, which we'll look at on the next slide. The coefficients are the exponents, and K is constant for a given temperature and unitless. So that means if the temperature increases, K changes. We don't know if it's up or down. That depends on the reaction. All right, with gases versus solid, there's a bunch of different factors that affect that ratio there. So K is the ratio. The product concentrations divided by the reactant concentrations is what the equilibrium law is mathematically. So now what we're going to look at is solids and liquids, why their concentrations are constant. We'll do this briefly. It's not the focus of the lesson, but we should talk about it. All right, so the equilibrium equation gives us a ratio of products to reactants. Okay, so as the concentrations change throughout the reactants, as throughout the reaction, the ratio will be the same at the end, right? And they're specific to one temperature. So what this means is throughout the reaction, right, if I draw that graph again, I'll just draw this one here, draw a different one this time. The ratio of reactants to products approaches a constant value once it hits equilibrium. But before that, the ratio is constantly changing. All right, so this only applies at equilibrium, and it tells us what there's more of, products or reactants, and we'll look at why that's the case. So in terms of types of equilibrium, all right, heterogeneous is where all things are in the same phase. Homogeneous are where they're, oh, we got that backwards. Let's just switch that up. We'll just do this. Homogeneous is where everything is in the same phase. Heterogeneous is when there are two or more phases present. And that's just the state that the molecules are in. Okay. So we said this already once. Solids and liquids are not included in the equilibrium law. We replace them with a 1. Right? And the reason we replace them with a 1 is because their concentration is not changing, so it has no effect on the position of the reaction. So let's look at why the concentrations can and can't change. For a gas, you can change its volume through compression. Right? If you have the volume, you double the concentration. The reason for that is there's less space for those particles to occupy, so they become more concentrated. So this shows that a gas's concentration can change. An aqueous solution's concentration can change based on the number of solute particles in the solution. Right? More solute or less solvent results in a concentrated solution. Lower amounts of solute result in a dilute concentration. For pure liquids and solids, they're so tightly packed together that they can't be compressed any closer together, so their volume is pretty much constant. Right? So the space they occupy can't change even under extreme pressures. So we say that their concentrations are constant. All right? A gas can be compressed. You can see that again there. A liquid and a solid cannot. All right? And if you'd like to, you can try pushing on a solid that's on your desk. The most you could do is crush it, which would spread the particles out. But you can't make that same shape solid smaller by compressing it. So lastly, we'll look at what the value of K actually means, okay, on the following slides, because it does give us some information. It tells us whether we have more reactants or products. And remember, in an equilibrium reaction, you'll have leftover reactants at the end. Whereas in a complete reaction, you won't. All the reactants get converted into products. So in scenario A, if K is far greater than 1, and that's why there's 2 greater than symbols here. Far greater than 1 means a factor of 100. Okay, so if it's 100, 200, 300, so be it. We consider it far greater than 1. The reaction proceeds towards completion. Doesn't mean that it hits completion. Right? And the reason for that is if we look at the ratio, it was simply products over reactants. So if the value of that fraction is large, which is what K represents, then that means that the numerator has to be large and the denominator has to be a small value. So in this case, the numerator is products. And if you have a large product concentration, that means most of the reactants were converted. So we can draw that graphically just to show kind of what happens over time. We'll do concentration on the right-hand side. We'll do a solid line for reactants and a dotted line for products. We'll keep that similar. So in this case, the product concentration has to be larger than the reactant concentration because the value is greater than 1. Right? So for that fraction to be true, numerator has to be larger. We always start with no products, right? And they increase. We can't assume the number because it depends on the reaction, so we're just sketching it. Ooh, and we've got that the opposite way. We're just going to, let's clean this up. So the reactants were going to be the solid line. All right. So we lose our reactants over time, and then they level off. Okay, notice again, they never hit 0 in equilibrium. And then our product reactant, our product concentration slowly increases. And once they hit equilibrium, right, is when the concentrations start changing. So we have more products than reactants. The ratio favors the numerator, so it's larger than 1. Right? So the K value tells us where we can expect to find these concentrations at the end. If it's approximately 1, anywhere from 0.1 to in the tens, 10, 20, 30, 40, 50, and so on, and remember it's unit list, they're approximately equal. So if we draw that out here where our reactants, our products, we've got our time, we've got our concentration in moles per liter, we lose our reactants, we gain our products, and they are approximately equal within the range that we've set out up there. All right, so the graph looks like this. And what this tells us is we use up, well, not always about half, but it just means at the end we have equal concentrations of both. Okay. Now, none of this means good, bad, it's just a property of the reaction. Some reactions you want to completion and some you don't, depending on the scenario that's being applied. So lastly here, where we say K is far less, is much less than 1, right? So remember what the ratio is, products over reactants, and we're just leaving the math out here. We're just focusing on the property of it. Because the value of the fraction is less than 1, so we say this is less than 10 to the power of negative 2, or 0.01, right? That fraction itself is very small, so that means the denominator has to be larger and the numerator has to be smaller. So I have more reactants than products. This is called an unfavorable reaction, right? Not a lot of it actually forms. So graphically, what happens, again, we're using the same units here, reactants and products. The reactant concentration changes very little, and then it levels out. And because very little reactants changed, that means very little product changed as well. So it doesn't mean we reach equilibrium earlier. It has nothing to do with the time or the temperature. It's just the ratio. So we have more reactants than products in this case at equilibrium, which means the value of K is small. The ratio is low. And a low ratio means an incomplete reaction, very little formed. Now equilibrium is funny because an incomplete reaction is complete if only 1 mole of your substance reacts out of 10, and as long as that 1 mole reacts, it's completed to what it's supposed to. It just hasn't converted all of that. So how do you know if a reaction is in equilibrium or not? There'll be information that tells us about that, depending on what the reaction is, and certain types of reactions follow equilibrium. So if it's observed to be reversible, then it's an equilibrium reaction. So what you learned kind of earlier, probably in grade 9 of your science education, even in grade 8 or earlier, chemical changes are irreversible, is not really true, and that's a misconception. What is true is that a chemical change is reversible. It represents just a change of the substance. Okay, so we shouldn't say that chemical changes are irreversible. This is proof that they are reversible. So that ends that there. You can have a try at those questions, very straightforward, just applying the equilibrium law to various reactions. And in part B, we'll plug some numbers in for those concentrations. All right, so thank you for watching, and see you in the next part.